Hello, my name is Abhishek Bansal. In this video, I am going to take the design example 2, and in this design example 2, the input would be an AC board that would be a 90 volt AC to 64 volts AC. The input line frequency would be either 50 Hz or 60 Hz, and we would be needing a 19.95 volts at the output at 3.25 amperes. So basically, this would I am going to again design using flyback. In the design example, I am going to use an active clamp flyback. So rather than going directly on the circuit, because now we know like what would be the circuit component. So what would be an IC that here I am going to use? Again, the vendor name I am not going to mention it because any vendor can be used. The particular IC would be or should be capable of an active flyback performance. So we are going to use an active clamp so that we recovers the leakage inductance energy. The IC also we are going to use a adaptive control for the fast zero voltage switching. So that means we are going to use ZVS and a active clamp flyback ACF here. So it is going to help the tracking as a dead time optimization. Okay, the particular IC that I am going to use it as a adaptable bus mode. So we are designing this flyback converter not on a simple flyback, but we want to design it using an active clamp flyback, and we are going to use the leakage inductance energy. We are also going to employ the zero voltage switching, okay, and they are going to track over our full load range. So once I am using an input as an AC, obviously we are going to use an common mode choke there with a diode rectifier. The common mode choke I will take in the common only, and here I am going to only do the feedback from the output and this active controller explanation. So the pin that the controller that I am using has one pin FLT. It's basically a fault pin, and the controller enters into the fault pin if the fault pin voltage is lower than the 0.4 volt. Let me draw something. Okay, let's go firstly by the pins only. So the pin, there would be an IC, and I am mentioning the pin number 1 is the fault pin. So the fault pin is basically, we are going to, if the fault voltage is basically pulled up 4.5 volts, or if we are going to pull below the 0.5 volts. So 50 microampere current source, it interfaces with an external NTC, because we are going to use a negative temperature coefficient thermistor here for the temperature sensing, and the current source is active during the run state and inactive during the wait state. A 50 microsecond fault delay, it allows the filter capacitor to be placed on the fault pin without force triggering the 0.5 volt, and the alternatively we can use a high resistance voltage divider that can be used to sense the peak bulk or to sense the bulk input capacitor voltage for the line over voltage detection. So 750 volts delay helps to prevent the force triggering the 4.5 volt line input line over voltage for the short duration. bulk capacitor voltage overshoot during the line surge and then ESD strike events. So this, when we are going to use this pin for the line over voltage detection, we can implement on the CS pin. The other pin is basically RTZ pin. That RTZ pin is basically we have to put a resistor between this pin and the analog ground, and it's going to program adaptive delay for the transition to zero voltage from the turn off edge of the high side clamp switch to turn on the edge of the low side switch. So the parasitic capacitance between this pin and the analog needs to be minimized to avoid effects on the dead time calculation. The third pin is an RDM pin. RDM pin, again we have to add a resistor from this pin to the analog ground, and we are going to program now synthesize the demagnetization time that we are going to use to control the on time of the high side switch to achieve the zero voltage switching on the low side switch. So the controller applies a voltage on this pin that varies with the output voltage, and it is going to derive from the another pin signal, and the parasitic capacitance between this pin and the ground, again we need to minimize it like in the previous, but here we have to minimize to reduce its effect or to reduce its influence on the internal PWM on time calculation. Next pin is IPC pin. Here the IPC is basically the intelligent power control pin. So to optimize the converter frequency or the converter efficiency, so the 50 microampere current source, it directly interfaces with the resistor to the analog ground, and to program an increase in the peak current level at very light load. Similarly, the burst frequency can be further reduced, helping to achieve the low standby power and the tiny load power. If this IP pin is connected to the ground or to the analog ground without a resistor pin, the peak current level in the very light load is set to a minimum level for the output ripple or inaudible noise sensitive designs. So we can also connect this if we are using the resistor pin for this, we can connect between this pin and the CS pin, or we can even connect this IPC pin directly to the CS pin. So our 50 microampere IPC pin create a output voltage that's going to be dependent on an offset voltage on the CS pin for reducing an output ripple in an adaptive burst mode and improving the light load efficiency at a lower output voltage level of a wide output voltage range design. So we need to one more, because I am taking an example of only a flyback design, but if we are going to design a power factor corrector PFC, we are going to design it at it can be used, we can disable the PFC here, PFC controller. If we are connecting, it can disable the PFC controller at all load condition of 5 volt, 9 volts output through the controller to further improve the light load efficiency for the high power adapters. The next pin is basically a BUR pin. This is a third fourth, and now we are talking about pin BUR pin. So the BUR pin is basically the burst threshold of the converter at. We are going to program the burst threshold of this converter at light load. So resistor divider between the this RF pin and the ground is you going to set the voltage at this pin to determine the peak current level when the converter is going to enter the burst mode. That is an basically this particular IC called an ABM. It's an adaptive burst mode. So in addition, the Thevenin resistance on this BUR pin is going to set an offset voltage for smooth mode transition. We can have a pull-off current of some 2.7 microampere and it's going to increase the peak current threshold when the converter is going to end in a lower power mode and 5 microampere down. The current reduces the peak current threshold when the converter enters into a heavy load mode. Adaptive amplitude modulation from this adaptive burst modulation. The sixth pin is the feedback pin that's going to close the converter regulation loop, and this pin is going to provide a 4.25 volt output that's going to have a 0 microampere or 75 microampere current pulled out of the pin, corresponding to the converter operating from full power to the zero power conditions. So we are going to have a 220 picofarad filter capacitor between the feedback pin and the reference pin to desensitize the feedback signal from the noise interference. The next pin is an REF pin that's going to be given a 5 voltage reference output. It's going to again require a 0.22 microfarad ceramic bypass capacitor to analog ground, and this reference is used to power internal circuits and can supply a limited external load current. So pulling this pin low shut down the PWM action, and it's going to initiate a restart. Okay. Next pin is basically a CS pin, that's a current sense input pin, and it's going to this pin is going to get coupled to the current sense resistor through the line compensation resistor to control the peak primary current in each switching cycle. So an internal current source on this pin is going to proportional to the converter's input voltage. It's going to create an offset voltage across the line compensation resistor to balance the level across the line. And this pin can also provide an alternative and OTP function when we are going to have the fault pin is going to use for the line input over voltage, and the small signal diode in series with an NTC thermistor is going to connect it between the PWM high and the CS pin to form the OTP detection. And when this PWM high pin is used, or PWM high pin is actually an high pin, so the NTC resistor and the line compensator resistor becomes a voltage divider, and it forms a voltage divider to forming a 5 volts, and it's going to create a temperature dependent voltage on the CS pin. And when the CS pin voltage is higher than 1.2 volts in the PWM high on state for the 2 consecutive cycles, the OTP pin default is going to get triggered. The 10th pin is a run pin. A run pin is basically the controller is going to run in a when we are going to hide the run pin, the controller would be in the run state, and the output is going to be low during the startup, wait, and the false states. And we have 2.2 microsecond timer delay that's going to initiate the PWM lower. This was the high pin, we have PWM low, switching after that pin has gone high, and the pin voltage above the 10 volts good threshold. So we have another this pin voltage threshold is another pin which is for this IC is S13 that I will take later on. I mean just after 1 minute. So the pull-up driving circuitry capability of both the run pin and the PWM high pin, it allows bias power management of a digital oscillator. Okay. So the power consumption can be reduced in a wait state. We have a PGND pin, that's a low side ground return of the PWML driver. The internal level shifter is going to allow the common return impedance to be eliminated, improving the high frequency operation. And if we are going to use, suppose the transistor is basically a GaN based gate injection transistor we are going to use. The pin can be connected to a separate source pin of the gate injection transistor, and this is basically going to enhance the turn-off speed and decouple the additional voltage spike on the current sense resistor and lay out the parasitic inductance of the gate driving loop. So for a silicon power FET, the pin is going to connect to the source for a smaller gate driving loop. For a GaN power IC with a logic PWM input, it can be referred to AGND. So now we take a PWM low pin, that's basically a low side switch gate driver output, and the high current capability is basically of the PWM. It enables driving of the silicon MOSFET within high capacity loading. Okay, so next is basically as 30 I have talked during the run pin. So this is basically coupled to there is one pin which is known as P13 pin. That's basically a 13 voltage output supply pin. P13, that's why it's called a P13. And this pin is coupled to this thing through an internal resistor of 2.8 ohms, which controlled, and it is controlled by the run pin. And when the run is high, the as started decoupling capacitors change up to 13 volts by internal soft start current limiter. So the S13 pin voltage needs to be increased from above the 10 voltage to initiate the PWM low switching. When the run is low, the S13 is discharged by the S13 pin loading. Okay, the power on delay of the IC on this S13 should be less than 2 microseconds to be responsive to PWM low. We are going to use a 22 nanofarad ceramic capacitor between the S13 and the driver ground, and it can perform power management of this PFC, power factor controller, which we are not using for this circuit. Okay, at the same time through a diode, and this power factor controller can be disabled at deep light load condition. So now we come to P13 pin. The P13 pin is a regulated 13 volt output voltage that derived from the VDD, and during the startup it's been connected to the VDD pin internally only, so that the external high voltage depletion MOSFET, it can provide the controlled startup current to charge the capacitor. After the initial startup, this recovers back to 13 volt regulation. Again, we need a 1 microfarad ceramic bypass capacitor. We are going to require to take it to the ground, and we have a 20 volt zener between this pin and an AGD pin. We have to use it to protect it from the overstresses when this connection between this pin falls open or a line surge energy is coupled to the pin. We have a PWM high pin. That's basically our PWM output signal. It is going to control the gate of the high side clamp switch through an external high voltage gate driver. The driving capability is designed to bias an external level shifting isolator through a small signal diode, or it can also transmit the signal to a high side driving circuitry through the pulse transformer. So the maximum voltage level of this PWM high is clamped to the 5 voltage reference level. Now other pin is the 16th pin. Now I am taking. It's an SWS pin. That's a sensing input, is used to monitor the switch node voltage as it nears the 0 voltage in normal operation for the ZWS or the 0 voltage switching auto tuning. So the source of the high voltage depletion MOSFET is coupled to this pin through current limiting resistor. So only the useful switching characteristic below the 15 volt is monitored. During the startup, this pin is connected to the VDD pin internally to provide the startup current. The external current limit resistor and a small bidirectional TVS across this gate and the source of the MOSFET, which I have just talked. We are going to use a depletion source MOSFET here. It has a depletion source MOSFET. So that should be added to protect the gate to source voltage from potential abnormal voltage stresses, and the resistor should be higher than the 500 ohms. The clamping voltage of TVS should be less than the voltage rating of this depletion MOSFET, but it should be greater than the 15 voltage. And the resistor and the 22 picofarad ceramic capacitor between the SWS pin and the bulk input capacitor ground form a small sensing delay to help the internal detection circuit to identify the 0 voltage switching characteristic correctly. The 17 and 18 pin is an XCD pin. XCD pin is basically a X-cap discharge input pin with a 2 milliampere maximum discharge current capability. The 6.5 volt line zero crossing threshold of this XCD pin. It is used to detect the AC line presence. When the line zero crossing is missing over an 84 millisecond timeout period, a discharge current is enabled for a maximum period of 300 milliseconds followed by a 700 millisecond no current blanking time for the last of fault protection. When AC line recovers and the line zero crossing is detected again, the controller can reset the lost fault state almost immediately and will attempt to restart without waiting to fully discharge the bulk input capacitor. For the auto recovery fault protection, if the controller is in 1.5 second auto recovery fault state, the line zero crossing can reset the timer and speed up the restart attempt. And the two redundant X-cap discharge pin is going to help to provide the X-cap discharge function even when one pin is in a fall open condition. So to form the discharge path, an anode of the two high voltage diode, it rectifier is going to connect to each of the X-cap capacitor discharge terminal, and the two diode cathode are going to connect together again to a 26 kilo ohm high voltage current limiting resistance, and the drain to source connection of a high voltage depletion MOSFET is going to couple the resistance to the XCD pin. So two series resistor we are taking a 13 kilo ohms SMD resistor here, and we are going to use it to the current limiting device and share the potential transient voltage from the AC line. Okay, so we are having a 6 volt rated MOSFETs, and it is going to be it's needed as the high voltage blocking device. The MOSFET is going to connect to the P13 pin, that's a regulated P13 pin, so that the X-cap discharge, it must be connected to the line 0 pin. If the X-cap discharge function is not needed, the XCD pins must be connected to the AGD pin to disable the function. The diode resistor MOSFET path must be then removed. Okay, now I am going to talk of the next pin, which is basically the BGND. It's a boost converter return pin connected to the source terminal of the internal 30 volt boost switch. The separate ground returns the simplified PCB layout design to minimize the high di by dt switching loop along with the boost mode and the VDD capacitor. So the noise coupling effect to the other sensitive nodes can be mitigated. Next pin is basically BSW pin, and the BSW pin is the boost converter switch node that's connected to the drain terminal of the internal 30 volt boost switch. For wider output voltage application, the boost inductor and the boost diode anode are connected to this pin. For a fixed output voltage design, B in and this pin should be connected to the ground pin. So we are having the boost. So the boost converter is basically disabled in order to lower the controller run start. We were going to use a 22 microhenry inductor with a higher than the 0.4 ampere saturation current capability, and less than a 1 ohm resistance is recommended for the boost inductor selection. If the maximum VDD pin voltage is less than the 30 volts or 30 volt Schottky diode, okay, is recommended as a boost diode. So the voltage stress from the diode reverse recovery effect can be avoided when the converter operates in the continuous conduction mode. The next pin is the B in pin, that's a boost converter input pin. That's basically for a wide output voltage. When the voltage is basically when the boost converter is needed to improve the converter efficiency. So B in is going to connect to the rectified auxiliary winding. We are going to use a 33 microfarad energy storage capacitor in parallel with a 10 microfarad ceramic capacitor, and the 33 microfarad capacitor should be placed close to the auxiliary rectification diode and the auxiliary winding ground terminal to minimize the rectification of the auxiliary loop. Okay, close to the rectification diode and then auxiliary winding ground terminal to minimize the rectification switching loop. So the 10 microfarad can be placed close to the boost inductor and the BGND pin to minimize the boost input switching loop, and together the Schottky type auxiliary diode less than 0.1 1.1 ohm winding resistance on the auxiliary winding is required to ensure the boost converter receives the sufficient transformer energy under a very low output condition. We are going to also use a unidirectional TVS between the pin to protect the pin from exceeding a 30 volt rating when the potential abnormal voltage surge occurs. And if suppose we are not for the design, as we are not going to use the boost mode here, we can connect it to the ground pin here. So the voltage sensing input is coupled to, we have another pin, that's a BS pin, that's the voltage sensing pin, and that's going to couple to an auxiliary winding of the converter transformer via resistor divider. The pin associated and the pin associated external resistance are going to monitor the output and the input voltages and the switching edges of the converter at the different moments within the each switching cycle. So the parasitic capacitances between this pin and the AG endings need to be minimized to avoid the impact of the output voltage sensing and the dead time calculation. We have a set pin. The set pin is going to configure the controller to be an optimized for the gallium nitride power FETs, or we are going to have a silicon power FETs on the primary side. Depending on the setting, it will optimize the parameters of the ZVS control loop, dead time adjustment, protection features. So when pulled high to the reference pin, it is optimized to the silicon FETs, and when pulled to the ground, it is going to optimize the gallium FETs. So the thermal pad must be connected to the AGND. So this basically I have talked on the active clamp controller. These are the features of the IC only. This is the feature of the IC only. So this IC basically is a transition mode active clamp controller. It's enabled with a it's controller. It's equipped with an advanced control schemes. So to enable significant size reduction of the passive components for a higher power density and then higher average efficiency. So its control law is going to be optimized for the silicon and the gallium power FETs in a half bit configuration, and it's going to be capable of driving a high frequency AC to DC up to 1.5 megahertz. So the ZVS is capable of auto tuning on the time side of a high side clamp switch by using a unique lossless ZVS sensing network connected between the switch node voltage and the SWS pin. The ACF controller is going to design to adaptively achieve the targeted full ZVS or the partial ZVS conditions for the low side main switch with the minimum circulating energy over a wide operating conditions. Auto tuning, it eliminates the risk of losing the zero voltage switching due to component tolerance, temperature, input output voltage variations, since the QH on time is correctly by cycle. So the dead time between the PWM high and the PWM low, they are optimally adjusted to help minimize the circulating energy required for the zero voltage switching, and therefore the overall switching system frequency can be significantly improved and the more consistent efficiency can be obtained in the mass production of the soft switching topology. Okay, so we have just seen that this IC in itself, if I have to draw an IC block diagram, functional short block diagram, I can say this IC has a switching regulator control. Okay, it's having a survival mode here with an auto balancing. I am drawing the blocks here. This would be fed with a PWM low. Okay, this is going to give the signal to our switching regulator control. Here, if I am going to use a boost here, this is going to be, it has an internal MOSFET here. Okay, here we have an under voltage lockout, VDD on and VDD off. Again, I need to draw a block to here. We have a power and a fault management. We have a ZVS control here block. We have a P13 regulator here. Okay. We are having an SR flip flop here. Let me draw as SR flip flop by SR flip flop properly. S R Q and a Q bar. This is an SR flip flop. This SR flip flop, this Q we are going to take to the PWM low. Okay. And here we have an OT detect and over temperature detection, over line, over voltage detection. There is a Schottky diode here. It's going to would be the input. This the fault pin would be here, and we are having an X cap. What I have talked of. This is an X cap. This is an OT block. This is an OV block, or we can have one block here. Okay, and we are having a CS offset. We are having a ZVS discriminator. We are having again an OT detection block here. We have an voltage sensing here. We have a thermal shutdown block here. And we are having a bus control block also here. We have one more regulator block here, REF regulator block. That's going to give us an REF. So now let us go from the designing point of view.